Oh, actually, I call it example 0. So it's called example 00. This is on my notes. Like this. What is this example? In this example, let's compare two different kind of failure modes. One is due to material yielding, and the other is called buckling. Suppose I have a column, and the column looks like this. And it's sitting on the ground like this. And suppose there's a hinge support like this. The column is subjected to an axial force. This external axial force looks like this. And the force is denoted by, you may call this force P. And the column has a height or span to be 100 inches. For example, now suppose that the column is made of structural steel A36. Now our objective is what? Is to evaluate the failure mode of this column. That's our objective. So how do we solve the problem? And the way I solve problems are usually taken by steps. So step one, let's understand our condition. So what is A36 structural steel? A36 structural steel means that the yield stress is 36 KSI. And as you remember, this is from steel design, right? Some of you probably remember A36 means the yield stress is 36 KSI. And what's KSI? Of course, you should know what KSI is, right? KSI, if you don't know what KSI is, KSI means kilopounds per square inches, right? So that's kips per inch square. That's KSI. What's PSI? That's pounds per inch square. Now for the 36 KSI yield stress, the Young's modulus for this kind of steel is 200 GPa. And GPa means gigapascal, and giga means 10 to the power of 9. So that means this is 200 times 10 to 9 Pascal. Of course, you cannot work Pascal with KSI. They're in different units. What's a Pascal? Pascal means newtons per square meter, right? So you know that you cannot deal with this. You cannot use 2 times 10 to 11 Newton per square meter. These two units, they don't work with each other. So we have to convert GPa to KSI. And for 200 GPa, this is approximated to be 29,000 KSI. That we know. So the first thing we can do in step 2 is to assume that in this column, there's no deflection. The column will not sway. When it fails, it will fail due to yielding. So we assume a yielding mode. when we assume a yielding mode, that means that the failure mode or the failure force is going to be the yielding force. So what's a yielding force? A yielding force is just Fy equals to sigma y times what? Times the cross-sectional area, right? So times the cross-sectional area. And I have not give you the cross-sectional area. So what's the cross-sectional area we have in this problem? Let's assume that this is a 10-inch by 10-inch column. So from here to here, you have 10 inches. From here to here, you also have 10 inches. And if you have a 10-inch by 10-inch cross-section, the cross-section area, of course, is just 10 times 10. That is 100 inches squared, right? We also need to know mass moment of inertia. And that's also what you learn from the first time it should be in statics, and the second time in dynamics, and the third time you use it is in strength of material, correct? So now, for a rectangular cross-section, this way you will not mess up with the B and H. We know that the mass moment of inertia, I, equals to 1/12 of B times H squared. So what's B? B is the dimension perpendicular in parallel to the axis of rotation. In this case, if we look at this plane, we assume that the bending is going to happen on this plane, which means that the axis is like this. This is your axis. And the dimension in parallel to the axis is the dimension we call B. So B is this dimension. This is B. And H is the dimension perpendicular to this axis of rotation. So this is what we call axis of rotation. That means from here to here is your H. Now you understand perfectly why I use 10 by 10. This way, nobody will make mistakes. Because B equals to H. So from here, we can come back and to calculate this value. And that means the mass moment of inertia of this cross-section is going to be 1/12 of 10 times 10 to the cube, right? Like this.
Cubed or square, because in the formula you have it squared there.
Thank you very much. It's actually EH cubed. Thank you for pointing that out. Okay. So one thing to remember this is what? Is mass moment of inertia is always fourth order of the length dimension. So we have one order from B, 3 orders from H. Altogether, that's 4 orders. And this result, if you have a calculator, you will know this equals to approximately to be 833.33. And of course, and this unit is in quadruple inches. Okay. So we know this. Now, if I know A, if I know sigma y, can I find out what is the yield stress or yield force? The yield force in this case, let's complete this step, equals to 29 KSI. No, actually it's 36, right? 36 times the cross-sectional area, which is 100, and that means this is 3,600 kips. So this is our first answer. By assuming that the entire column will just yield, and the failure force or the failure load will be 3,600 KSI, kips. Now, but it so turns out that there are other modes. For example, one mode is this. Suppose the loading, the force P applies from the top, but somehow there's some disturbance, or somehow that the column has some inherent imperfection. That means The material is not uniformly made. When you apply the force, there always some force actually applied to the side. That means when you apply the force vertically, there's a possibility that the column could actually bend. Would you agree? Especially when the column becomes very long. You must have that from your everyday experience. You probably wouldn't do this. If you want to support a floor or support something with a very heavy mass, you wouldn't want to try to support that kind of load with a slender bar, right? Just imagine that, I don't know if you can see me, and you wouldn't want to support something very heavy with this, correct? Because if the column is so slender, there's a tendency that the column could actually bend. So that possibility is another failure mode. And that failure mode associated with what? With the geometric change, which means this, which means it is possible that this column could actually bend like this. It will actually bend like this. Now from steel design, you already have this equation, or just use that equation for now, because I haven't shown you how we actually got this number. But from there, we're going to use the equation that we know. We're going to say from steel design, we have this equation. Critical load PCR, or we call buckling load, equals to this, equals to pi squared times EI divided by L squared. And pi is, of course, is the circle pi. If you plug in the numbers we have here, it becomes pi squared times the Young's modulus we have is 29,000 times 10 to 3. And the Young's modulus, that's 29,000 times 10 to 3. The mass moment of inertia is 833.33. And everything divided by L squared. And L here is 100 inches, right here. One to 3, A by 1.45 kips. Is that right? And of course, this result means what? This result means that this number is going to be, and the result is opposite. It's greater than this. And that means here, the values we're looking at here will become different. It's going to be, the lower value now becomes 3,600, and the higher value is 23,000. So one is a 3.6, the other is 23.8. And so if we just mark these two, 3.6, we say this is times 10 to 3. And the other one is 23.8. That means is this value here.